Okay. So while we are going to continue with the, so what we are discussing basically, we are discussing the frequency and duration model. Okay. So frequency and duration model. This is the problem that we had taken into consideration. And for our problem, what is important is the lambda or failure rate is 0.01 and mu, which is the repair rate, which is 0.49. Okay. For our case, all the generators are identical. Therefore, identical in terms of hazard rate. So lambda 1 and lambda 2, lambda 3 is equal to 0.01, mu 1, mu 2, mu 3 is equal to 0.49. Okay. So this thing you mentioned in your note, again you have not mentioned lambda 1, lambda 2, lambda 3 are 0.01, mu 1, mu 2, mu 3 are 0.49. So what is the concept of frequency and duration approach? In the frequency duration approach, okay, first we do a state diagram, state space model. Okay, we find out the states. In this case, there are 3 generators. Therefore, there are 8 number of states. Okay, and each generator can be either up or down. Each generator can be up or down. Okay, and we are considering only single state transition. So that means, suppose there are 3 generators having particular state, only one generator can undergo a change from up to down, down to up or vice versa. So we are considering single state transitions. Single state transitions. Okay, that's it. So next we have developed this model. So we Markov diagram class. We have created this model where each generator has certain number of states. Okay. Then that was represented by means of this, and we discussed in the last class that this transition, suppose from 1 there are 3 ups, so we can go to only one transition. For example, to 2, because here generator is up is now down. Okay, and what should be the departure rate for this case? Lambda 1, because unit 1 is now failed, so this 0.01. Okay, but then you have to also find out what are the other single state transitions and then combine them. As an example, we saw that from the state 2 we can go to either state 1 or 5 or 6, where in state 2 to 1 involves repair of unit 1, state 2 to 5 involves failure of unit 2, state 2 to 6 involves failure of unit 3. That means lambda 2 plus lambda 3. So accordingly,
sir, it kept out the 25, 50 megawatt.
okay, so this is capacity out. Okay, capacity out. What is the capacity of unit 1 in the question? 25. Second? 25. Third one? 50. So it says that all the generators are up and running. So that means capacity out is 0. Okay. Now here only generator 1 is down. That means capacity out is 25 megawatt. Right? And here generator 2 is down. Capacity out is again 25 megawatt. Here there are 2 generators up and 1 generator down. That means this should be 50, right? No, this is 55, because for unit 3 the capacity is 50 megawatt. So when unit 3 is out, capacity out is 50 megawatt. Here unit 2 and 1 are out, 25, 50. Here 1 and 3, 50 plus 25, 75 megawatt hour.
Sir, 4 দুইটা অফ হচ্ছে, দুটো ডাউন হচ্ছে 50. তো
up means it is running, down means it is out.
2 রে भी तो सेमती होছে, দুটো ডাউন দুইটা
because capacity is different. 2 ray capacity is 25 megawatt, whereas generator 3 has capacity of 50 megawatt. Got it? Here, so here all are down, so total capacity out is 100 megawatt. Right? Okay. Now this calculation we have done manually in the last class. Let's see how it is performed. Okay, so this is the whole thing. Okay, and we have seen this part only. Okay, from state 1 there can be 3 departures only. Okay, for generator 1 or generator 2 or generator 3. We are not considering AND. Okay, we are considering only single state transition. So for different states, these are the transitions. Okay. Okay. So what is the total departure rate? It is the summation of these three. Is the summation of these three. So to understand this concept, okay, to understand this concept, we will take a random state. Okay. Suppose we consider state number 4. Okay. State number 4. So state number 4 you will see here. 1 up, 2 down, 3 down. Okay. So what are the transitions from state number 4? If generator 3 is down here, if it is repaired, we go to state 1. Other two remains the same. Therefore, the transition rate is mu3, the repair rate of unit 3. Okay, mu3. What is the other transition? Now we can go from we can go from this state 4 to 6. So this was 4 to 1. 4 to 1 involving generator 3. 4 to 1 involving generator 3. Right? Then 4 to 6 involving which generator? One. Generator 1. Okay. And what is the other transition? 4 to 7. Generator 2. 4 to 7 is generator 2. Okay. Now we will consider generator wise 1, 2, and 3. So for 1, what is happening from 4 to 6? Go down. Down. That is lambda 1. From 4 to 6. So sorry, this is done. This is done. 4 to 1. 4 to 7. Okay. So this is done. So this is for generator 1, lambda 1. Next is generator 2, 4 to 7. What is happening? 4 to 7. How is down? 2 is down. From 4 to 7. 2 up, 2 down. So this will be lambda 2. Okay. And for the third one, 4 to 1. So down is down. So mu3. Okay. So this will be lambda 1 plus mu2 plus mu3. What is lambda 1? 0.01. Lambda 2 0.01. mu3 is 0.49. So that is 0.51. So we cross check that with the SSC. So state 4 UUD and the transition rates are I think this one, right? 01, 49. Right? So total transition rate is 0.5. Okay, departure rate. So the first thing that we saw here is write down. First point is departure rate. Okay, departure rate. Okay. So the first point is total departure rate. Okay. Now, what is our objective? Our objective is to find out duration and frequency. Okay. Now, how to find out the duration? That means, what is the probability that one is duration? The other part is duration. Okay. Duration. So, what is the probability that generator 1 is up? No. You see the question, there is one FOR. Okay, so what is the FOR? 0.02. That means what is the probability that the generator is up? 0.98. And the probability that the generator is down is 0.02. And it is same for all the generators for a simplified case. Okay. So with this information, we will find out state probability. Okay. So first one was departure rate. The next is what is the probability of this state? What is the probability of this state? So the probability of this state is equal to probability that the generator 1 is up and probability that the generator 2 is up and probability that the generator 3 is up. Okay, right? So what is the probability that the generator 1 is up? 0.98. 0.02 is failure rate. It is down. FOR, forced outage rate. So that means the probability for unit 1 is 0.98 because it is up. Probability for unit 2 is 0.98 because it is up. Probability of unit 3 is 0.98 because it is up. Now since the whole state is a combination of all these three states and we consider and according to probability theory we will multiply these three. So if you multiply these three you should get this. Are you getting this? If you multiply 0.98 into 0.98 to the power 3. 0.98 into 98 into 98. So we are getting that? Okay. So this is the state probability. Okay. First term we saw was departure rate. Departure rate means if the system is in state 1, what is the departure rate for it to go to any other state? It can go to 2, 3, 4, whatever, depending on the generator up or down. Okay. Second thing we saw that what is the probability that the system is in current condition. Okay. Up, 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 down, 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 or whatever. That is known as the state probability. Okay. So two things you saw: departure rate, state probability. And the last thing that is important for frequency and duration approach is the frequency of encountering a particular state. Okay. One is the probability of obtaining that state. The other one is frequency of obtaining that state. So how to get the frequency? That is the third point. So the third point is state frequency. Third point is state frequency. So the frequency is equal to what condition you are in. What is the probability? For example, what is the probability that all of you are in the classroom? Okay, that depends on the availability of your individual probability. It's a multiplication of all the individual available probabilities. Okay, so that is the probability that you are available in the classroom. Okay. Now, what is the probability that in another class all of you will be the same state will repeat. The same state will repeat. That means all of you again be available in the same class. Okay. For that we need to know what is the condition of each one of you. Okay. Depending on today's class, how many of you want to come to the next class? That is departure rate. That means this state of the classroom can transition into some other state. Okay, and we will consider for simplicity only one transition. That means only one person will decide whether you will come to class or not. One person will change. Okay, that is the departure rate. So if you multiply the current probability with the departure rate, then we get the state frequency. The frequency of encountering a particular state within a particular duration. So write down state frequency is equal to state probability. State frequency is equal to state probability into departure rate. That means if you multiply 0.94112, which is the state probability, with the total departure rate 0.03, you should get this number. Are you getting? Cross checking. Getting? Yes. So similarly, all the state probabilities when multiplied with all the frequency of encounters, all the departure rates, you get the state frequency. So this model is known as the frequency and duration generation model. frequency and duration generation model. Clear? Okay. So next, what we get after this question comes in the exam, will come as an 8-mark question. So there will be 2 parts, 4 plus 4. So this question will be a complete 8-mark question. It comes in the exam. FOR value may be changed, so you have to recalculate. When the FOR value is changed, you have to recalculate. Okay. If the lambda and mu are also, I will give you different values. 0.01 I will give 0.015, then you have to recalculate. But if it comes, it will come as an 8-mark question for all the states. Okay. Now, whatever here is there, the remaining part, okay, those are related to the reduced states generation model. Not very important. You can go to it. I have given in the PPT. Okay, it just we have got so many things, right? 0, 25, 25, 50, 50, 75, 75, 100. These are the so many generation states. These are what? Outage, capacity outage. What is generation model? In reliability, power system reliability. In power system reliability, generation model means a particular outage and what is the corresponding probability. That is the capacity outage. That is the generation model. Now, in frequency division approach, along with the availability or probability, we also provide the frequency. We also provide the frequency of the approach and the departure rate. Okay. But here there are same thing is repeated. For example, probability of 25 megawatt outage is this two, right? The system can remain in this state or in this state. So what's the probability of 25 megawatt capacity outage? So we add it or we multiply? Add, because the system can stay in either state 2 or state 3. It cannot stay in the same state at the same time. Only in quantum physics we do that. Something can stay in multiple states at the same time. But normal situation outside the quantum world, okay, everything can stay in only one state. Multiple states are not possible. So in this case, we add this 2. If you add this 2, how much are you getting this? Probability. Are you getting the state probability? You add those 2. Similarly, we have got 250 and 275. We add up and we find this probability. Okay. Now this is for probability, state probability. For state frequency is not that straightforward because frequency we cannot add up or multiply. Okay, that is the formula for that, which I have given in the slide, cross check. Okay, how it is to be calculated. So we go to the PPT and complete the rest. Okay. So we started from a 8-state model because there are 3 generators and each generator has 2 states, up and down. So we have 2 into the power 3, 8 number of states, and we can have single state transitions. Then we saw the departure rate or rate of departure from one state to whatever number of states it can go. It can go maximum 3 because there are 3 generators and we are considering only single state transition. Okay. And how to find out the frequency of departure? The probability associated with each state can be calculated as the event dependence. That is 0.98 into 19 into 19 that we saw. The frequency of enthalpy is the output is 1 when rate of departure or entry is the sum of appropriate states. What is 1? A into lambda. A here is probability. Probability into departure rate. Let's say only factor we are considering, so it's written like that. Okay. That is the formula that you have written. Departure rate into state frequency is equal to departure rate into probability. The result table contains a number of capacity states. So this is the generation model. So what is the generation model? The resulting table. The generation model is a table. So kind of the generation model in frequency and duration approach is a table. The generation model in frequency duration approach is a table which contains a number of capacity states which can be combined using the following equations, where the subscript I refers to identical states and K refers to the new or merged states. Okay. So summation. Okay. Yes. Frequency also you need to add according to the formula I have told you. This I showed you how to obtain the state probability by adding up in same capacity states and again adding up the same frequency. Okay. But departure rate, which is mentioned here as lambda plus minus a, has to be calculated using. Okay. When you combine the states. Okay. So we have seen this shape and we have seen the solution. Okay. So this essentially completes the frequency and duration generation model. Now we'll see some additional things about this frequency and duration approach. Okay. Some theoretical aspects. Okay, so cumulative probability and frequency. The generation system model often so far gives the probability and frequency of having a given level of capacity post out of service and the complementary level of capacity in service. Okay, so this is what typical generation model in a relative reliability or reliability means. Okay, the generation system model can be modified to give cumulative probabilities and frequencies. Okay, so at any given capacity level, the cumulative values given in the probability frequency having that. This you write down. What is the significance of cumulative that we have seen during LOL computation? Okay. It's the same concept that the cumulative value simply means the capacity or the probability of frequency having that capacity or more post out of service. That's why we start with 1 at the top, not at the bottom. The cumulative 1 at the top because of this. The individual state probabilities and frequencies can be combined to get the cumulative values using the following equation. So we have to use the following equation. For the probability it is straightforward, but for the frequency you have to use slightly different formula. Okay. So this formula you can apply to the Excel sheet and you can see how the cumulative values are computed. Okay. So quickly we will complete. So this is the complete system model. So first lesson 12 is related to the generation model, which is more important. Okay. The above will just summarize the above equations. N refers to cumulative state is known probability and frequency, and A is the state which is being combined from cumulative state n minus 1 to obtain this cumulative part. The transition value lambda plus k minus k at the transition stage to higher or lower available capacity levels. The process starts from the last state, that is in which the individual and cumulative values are the same. The generation system model so obtained can be used directly as an indication of the system generating capacity adequacy. So what we are actually evaluating? We are evaluating generating capacity adequacy. This approach is known as loss of capacity method. The final table contains both the, what is the final table or the final approach? The final table contains both the cumulative probability and the frequency values of each capacity level and can be considered as a complete system capacity model. Omitting the frequency aspect simplifies the development of the system capacity model, but with the attendant loss of some of the physical significance of the model capacity level. So frequency, as I told you, most of the places it is only the probability part that is used, probabilistic approach. Frequency approach is generally not used, but wherever required, if you require that in your thesis or project work, then you can use that. Okay. So this is all about the system capacity model or the generation model. So what should be the next part? Logically, reliability model consists of two parts. First is the generation model. First is the other one, load model. So in probabilistic approach, we have seen two kinds of load model: load duration curve and normal peak load, daily peak load variation curve. Two approaches we have seen. So here also we have certain load models, but again, as I told you, frequency approach is not very frequently used. So we'll just have a look. What are the various? There is some difference related to the load model. Okay. So that is the topic of. So that lesson 13 mostly will be a theoretical part. Okay. System risk indices. So that means. So what are these indices? We have got generation model plus load model, then only we get this indices. What are the risk indices that we discussed in the module 1? What are the risk indices? I told you those are the most important part of power system studies, planning studies. Loss of load expectation, and the other one was loss of energy expectation. Okay. So the risk indices are basically, even if you join some organization like OHPC, OPPC, etc., you will be always encountering these two terms. LONE and LOE will always be there in front of you. All planning studies are based, as of now, are based on this LOE and LOE. Now we see what are the various load models in frequency and duration approach. Okay. I'll just go through the slides. The generating capacity models can be combined with the load to obtain the system risk indices. Always remember this. The generation model as such is not of very significance. Only when you have a load model, you combine them and then you get the loss of load indices. As a basic probability method, there are a number of possible load models. So what are the load models? One is cumulative load model or load duration approach. The other one is individual peak load model. And assumption is made that load state transition occurs independently out of capacity state transition. We are considering load and capacity completely separated, so that we can combine them with normal independent event criteria. Okay. Frequency and duration analysis is normally done on a period basis, as the assumed constant low load level and random peak load segments do not usually apply for a long period of time. So for a short duration, it's kind of a dynamic study. Okay. Whereas probability approach is a static study, it's a planning study. Okay. So you have seen the daily load model for probabilistic approach. We have seen peak load model. So typical, you draw this. A typical load cycle or daily load model in frequency duration approach looks like this. Don't write anything, just draw the figure. So we have some load like this, but we change that to two different states. Okay. Two-state load representation. So what we do is a two-state load representation. Now here we will say the peak load is available for a fraction of time known as E. The peak load is available for a fraction of time known as E. Okay. So the daily load model contains a peak load level of mean duration E and a fixed low load of 1 minus E day. Okay, so during a day we have peak load for 3 hours and off peak or zero load for 1 minus 3 hours. And this is what we will consider for computing the risk indices. Done? That was daily load model. Then we have got a peak load model. So during a duration, we have several such peak loads. Okay. Then load cycle for a specific period shown above. Each peak load returns to the load level each day before transferring to another peak on the next day. The element E is known as the exposure factor. So one two more question may be asked in exam. What is this exposure factor? Okay. And why it is significant? So some examples is given. And then this period load level that you have seen, there are several things which can be defined. No numerical should be asked in this. So we have several such things like number of load levels, number of peak loads, low load, number of occurrences, mean duration, probability, upward departure rate, forward departure, downward departure rate, frequency. So all these things are combined, provided when you do some say project work which involves this frequency duration approach, then you might have to define all this. Next question is what are margin states? The combination of discrete levels of available capacity and discrete levels of system demand or load creates a states of discrete capacity margins. Okay, that means how much generation you have available and how much to lose, so that a loss of load occurs. That's known as the margin state. So what is the margin? A margin is defined as the difference between the available capacity and the system load. The negative margin has to prevent the state in which the system load exceeds the available capacity and depicts the system failure condition. A cumulative margin state contains all the states within the margin less than equal to system result. A margin state Nk is a combination of the load state Li and capacity state Cn. You just write this equation. Okay, Nk is equal to Cn minus Li. Just write the equation. The rates of departure associated with margin state are as follows. Okay, so there is another slide in the Excel sheet, another tab in the Excel sheet which shows this margin state. I have not computed that specifically, it's not very important. You just need to understand what is margin state. Okay? Did you write these two equations? Only these two equations you write? Next is individual probability and frequency of margin state. You can compute this. Okay, formulas are given and cumulative. All these formulas can be implemented. These are not very complicated, but no need to do this. I told you from sequence and union approach, I will ask you only with respect to the generation model. Okay, this is one example of how load is combined, okay, to obtain various margin states for frequency union approach. Okay, this is the second example. With another example here. Margins. So margin states are shown here. So eventually we have to compute the LOID. Okay, how it is computed, it is provided this. You have to just need to understand. So this completes frequency and division approach, and in module 2 only we have one part left, which is interconnected systems, that we will see in the next class.